All right, so hello everyone. We're going to be doing a little article review. The article is called Rust versus Go in 2025. So this article came out in January, 1st of January 2025. So it's been pretty much a year since it came out. And I've just come across it now, so that's why I'm doing the review now. And I thought I'd, read it. I've read the first 2 points. I haven't really gone much in depth. So this will be a sort of a react video in a way. So here we go. Which is better, Rust or Go? And does that question even make sense? Should you learn one, the other, or both? Which language should you choose for your next project and why? How does Rust compare with Go in areas like performance, simplicity, safety, feature scale, and concurrency? So this article is going to do a high-level overview, I guess. Like, what should you use given a very high-level view of your requirements, taking into account presumably these aspects of the problem you're solving. So I've already read this. It just goes over, like, hey, Rust is powerful, rich, Go is small, easy to learn. And then it also makes this sort of bumper sticker phrase, which references, hey, so why would you learn Rust if it's harder? Well, because it has to work. If you're writing in Rust, it's because it has to work, because Rust gives you these very powerful guarantees about your program, allegedly. So Rust and Go are both awesome. So great and horror. So this is humble and pragmatic. I assume if you're watching this video, you already are familiar with Go and Rust, sort of the features they have. In any case, this paper article will dive in. I want to get into, the sort of meat of the article, which starts here, Memory safety. Historically, one of the biggest causes of software bugs. Rust and Go, they do things differently here. Go does have a garbage collector, but they're both memory safe. And this has nothing actually to do with memory safety. This is just like the memory model of Go and the memory model of Rust. So if we go memory model, Go, RSC, we can read more about that here. There's some great sort of articles written by Russ Cox on how the Go memory model works. I think this one's a generic, just introduction into memory models. And he does go into, how the Go design and how the Go memory model works and the changes they performed around this time, which was in 2021. All right, enough about that. Memory safety. They're both memory safe. Rust doesn't need a garbage collector. So that's nice. It means your program will not have interruptions during runtime, or much more reduced, because Rust doesn't need one, but you do have, like arc, mutex, Rust, arc and mutex, atomic reference counting. Truth is, I don't know much about this, but there is reference counting in Rust. The overhead is basically negligible. Anyways, fast, compact executables. And I'd even go as far to argue as you don't need a garbage collector with Go, at least the way I program it. Same as in Rust, you don't need one. You can use one. But the truth is, most of the software in Go is written with a garbage collector in mind. It's just the ecosystem has just been built on the provided garbage collector of the runtime, that global garbage collector. So fast, compact executables, we know and love how fast Go builds. And both Rust and Go run extremely fast. And let's look at some benchmarks. So these are benchmarks which are designed so that basically the language features do exactly the same thing. And we see, so native Go has much higher runtime compared to Rust. If you use TinyGo though, you will get faster programs than, say, Rust. In general, always actually, you'll always get a faster program when you use TinyGo than when you use Rust. This probably doesn't take into account a lot of things, because these are simple examples, right? Where you're not depending on the standard library. Go standard library, like in my opinion, depends very heavily on the runtime. So if you are using the standard library, your results might differ. I'm not familiar with the Rust standard library, but overall, your programs can run faster than Rust programs. And I'm not sure about the size. I think there is a benchmark on size here, but it's not graphed. But when using TinyGo, your program are very small. Should be as small as Rust. In fact, there is a paper that shows Rust executables are 3 times larger on microcontrollers than Go executables. So you can find that. So this is a paper, and the flash used up by TinyGo executables is 3 times smaller than Rust executables. And C. Yeah, check that out. Videos linked in the description probably. General purpose languages. They're both general purpose, both have great standard libraries. I'm not familiar with the Rust standard library. The Go one is known to be excellent, although it does allocate too much, in my opinion, but it works for people. Then there's pragmatic programming style, pragmatic languages, neither strictly object-oriented. We can debate about what an object-oriented language is, but it's fair to say the style of object-oriented programming that C++, Java, C# users would expect is not present in either Go or Rust, thankfully. Yes. Go's objects are interfaces, and everything else is a concrete data structure. There's very little concept of abstraction in Go. There is generics in Go, so that would be templating or type parameters, depending on who you ask. It's all the same feature, but if you're using a good enough compiler like TinyGo, type parameters are optimized away and they are not virtual during runtime. Development at scale, that's what Rustaceans would call a zero cost abstraction, which are very present in TinyGo when using TinyGo. Development at scale, both Rust and Go have some useful features which make them suitable for programming in the large, whether that means large teams, large code bases, or both. For example, I got my feelings, I'm not sure about that. For example, both Go and Rust use a standard code formatting tool, Go FMT for Go, Rust FMT for Rust, putting an end to useless arguments over who put your brackets. This is great, but you're preaching to a choir here. Both have excellent built-in high-performance standard build and dependency management tools. No more wrestling with complex third-party build system or having to learn new ones every couple of years. Coming from Python, where every year you get a new de facto package manager. This is great. I will comment, Rust is known to size of cargo cache. Rust is known to have large, not binaries, but your build cache just gets so big. And I think from what I've heard, cargo suffers, the cargo ecosystem suffers from the same problem as NPM, where people just use packages upon packages, and you got like these long dependency chains where you just include everything when including, some package. I don't know enough about the cargo ecosystem. I'm tempted to say Tokyo or that other one, Serde, but I think that they might be so used that they've tried to reduce their package footprint. But yeah, this is a thing. People do complain about this. You don't have that problem in Go. Not sure why, but the Zen of Go, Go aphorisms, a little dependency. So this is one of the aphorisms Rob Pike sort of dependency. We prefer to copy over include dependencies in Go. So some might feel it's a terrible thing to do since you're stealing. You could give this person credit. Well, Go is an engineering language. Like we'd rather steal and not give credit. And I've had this happen to me. My libraries are short and sweet, and they're just so ready to be just extracted and just copy pasted single file libraries into a project without any credit where credit is due. Maybe a little comment here or there, but yeah, that's the thing we do, and it results in just a nicer ecosystem experience. No 90 gigabyte cache. Moving on, building Go and Rust code, having come from a Java and Ruby background in my earlier career, felt like an impossible weight off my shoulders. Preaching to the choir. Yeah, it's great. It's not perfect. It's good enough for engineering. It is state of the art. It's the best I've seen. It does have its ups and downs. Go package manager, the module system, but in spite of those flaws, it works better than anything I've ever seen. Performance-wise, both Go and Rust are very fast. However, Go is primarily designed for speed of development, including compilation, rather than speed of execution. The Go compiler doesn't spend a lot of time trying to generate the most efficient possible machine code. It cares more about compiling lots of code quickly. So Rust will usually beat Go in runtime time benchmarks. Will it though? It will if you're using the Go compiler, which is optimized for compile time speed. At least that's one of the features it's optimized for. But if you're using TinyGo, that is not the case. So you do have an option if you want, if you prioritize, what would that be? Performance over compile time duration. Rust's runtime performance is also consistent and predictable. So if we look at this, there's another paper which dives into the intricacies of real-time operating systems and the TinyGo runtime, and it shows TinyGo has no jitter compared to Rust, C, C++, and MicroPython. You do have access to even more predictable runtime than Rust if you use TinyGo. And yeah, I mean, you can avoid using garbage collection. So that's something I do talk about in one of my videos, where TinyGo flag would be the print Alex. You can pass the compiler flag print Alex to show all heap allocations. Using this, you can eliminate heap allocations in your program using the instructions, the tutorials on how to do that, given in my other videos, the TinyGo code review. Go's garbage collector is very efficient and optimized to make stop the world pauses as short as possible, getting it shorter, but garbage collection inevitably introduces some unpredictability in the way programs behave, which can be a serious issue in some applications such as embedded systems. Now, I've used TinyGo and C in embedded systems, and I can say with utmost certainty that using FreeRTOS, the supposedly real-time operating system, has been more unpredictable than the TinyGo scheduler. And I believe this is due to how simple the TinyGo scheduler is in comparison. When you have a fixed number of Go routines in your program is going to be completely predictable. And it's going to show no jitter, as we've seen here. I'm not buying this. I mean, yes, I do buy it if you put in garbage collection into the equation. But if you're using garbage collection, you probably don't care about your program being predictable. You can write programs without garbage collection. That's why we have this. If you want to know which operations allocate on the heap, so you can eliminate those, you can effectively eliminate heap allocations in your program by just making sure everything's on the stack or in a global variable that's initialized at the start of your program. Because Rust aims to give the programmer complete control of the underlying hardware, it's possible to optimize Rust programs to be pretty close to the maximum theoretical performance on the machine. Again, maximum theoretical performance. Zig seems to be approaching that much better than Rust is. This makes Rust an excellent choice for areas where speed of execution beats all other now you can go ahead and now you might be thinking, oh, might this be like an artifact? Is Zig like we've been running this benchmark for some time now, and we've seen this behavior. We've seen Zig outperform every other language consistently for the last 2 Zig versions. Zig is presumably approaching the maximum theoretical optimum runtime. Much better than Rust is, as you can see in this in this graph right here. I love that feature of Arch, making your mouse big. So, to sum up, Rust makes a number of design trade-offs to achieve the best possible execution speed. Questionable. By contrast, Go is optimized for simplicity and speed of compilation and is willing to sacrifice some runtime performance for that. Yes, garbage collection does sacrifice some performance, but you can do without it if you so wish to. Your choice will depend on whether you spend more time waiting for your program to build or waiting for it to run. I think here your choice, if you wish to be short on running, hey, use TinyGo and just eliminate those heap allocations if you care about predictability in your program. And if you're running on embedded systems, then for sure eliminate those heap allocations at runtime, not initialization, because you want your program to live forever, because you don't have an operating system to really manage your memory as well. And the TinyGo garbage collector is still iffy. Nia has been working on it lately. If I were to open up here TinyGo repo, but let's not get off track. Simplicity. It doesn't matter how fast a programming language is if nobody can figure out how to use it. Go, now I've already read this part, and I think this perfectly sums up this part, right? Like, so Go is a small language, little syntax. Go's specification is famously short, right? You go here, this is the entire specification in one web page. Now, it used to be 80 pages, but now it's gone a bit bigger. It's 120. And that's just full size, No, this is a pretty large font size. That's 120 pages of large font and you're using up all your margins here, which actually makes, yeah. So you're using up all your margins, which would reduce the amount of pages you use. So I guess it balances out. So 120 pages, 120 sheets of paper for the Go entire specification. Now Rust, on the other hand, Rust specification length in pages will Gemini, no official. Yeah, that's unfair though. We do have the Rust reference, so shoot. I've done the actual calculation for like the specification for Java, for C++, for C, for Python even. Python's also around 170 pages, but you famously can't implement Python consistently from its own specification. The specification notes that. I wonder if has anyone ever done the calculation of the Rust specification length? Doesn't seem like it, but I can guarantee you it's longer. Anyways, I don't need those numbers to show you what I'm getting at is features, right? Rust is a rich, expressive language. Any other feature you can imagine in a programming language. Beautiful. And you can do stuff like this, which I find it funny that they chose to show this exact example right here, right? The prime, is this a prime sieve? I can't even tell. It's like a match n, any. So 2n factorial, no, 2 to n. So that's a for loop, implied for loop, and anyone that matches, that's the argument, where n modulus d is 0. So iterates every number from 2 to the number itself. Could do divided by 2, right? And if it matches, then it's false. But this is very hard to read. I had to spend quite some time here reading it. I've never read this kind of syntax. I do know the match statement, but this is always this is. I mean, is this a method on integer on a range expression? Anyways, this is not code I'd want to run into, especially if you have more. If you have more of these, this could be seriously hard to read. This would only work if you have like one statement or two statements where cases where you have to do some expression magic. Any more and you'd and just making stuff hard to read. Why not just do a for loop, right? Did you really have to save up that much, those 3 lines of code? Is that 3 lines of code? Online Go REPL. Is func is prime and int bool, right? For I is range is equal to 2 from 2 I is less than n, I plus plus, if n modulus I is equal to 0, then I shift entered, return false, return true. And I have to catch if n is less than 2, return true, right? And so, okay, hello is prime 2, is prime 27, is prime 33. Oh, that's 9. That's divisible by 9. So 29 is the famous prime I'm looking for. All right, yeah. Was it worth it? No, you decide. I don't think it is. On the other hand, the complexity of Rust and its new way of thinking about problems that it requires makes experienced Rust developers expensive, and it can take longer to ramp up junior developers to a level where they can be productive. Rust might not be the best choice for projects that need very rapid development or prototyping, or where a cost is a bigger factor than safety and reliability. So yeah, it goes into this spiel about reliability and safety. And I mean, yes, default Rust is safer and more reliable than default Go. But honestly, if you program it in Rust and you learn the mental, and you get a feel for the mental model of Rust, you can then move over to Go and apply that reasoning. Instead of having things be pointers all the time, you can start thinking about structures where you embed types which are not pointers, like I've been doing in my networking user space stack. You look at something like this, and all these are concrete types, and you don't see a single pointer anywhere. None of these things are going to be nil at runtime, and you can program this way. There's nothing that tells you, oh no, this is not the Go way. No, we gotta have a new function for stack Ethernet and a new function for stack IP. All new functions return pointer types. That's something we made up along the way, I feel, from day one of Go. There's no reason we should keep doing things like that. We can do things better, where we don't just put a pointer type on everything and just be more mindful about, hey, using the 0 value of your concrete type, making the 0 value of your huge struct, stack Ethernet struct, be meaningful. And GitHub can't find what I'm referencing. So yeah, I guess that's sort of my takeaway. So it's a shame that people have this sort of view of Go and Java and all these languages because, you know, nil pointer exceptions. And yeah, it's true, nil pointer exceptions are much more common in languages like Go than Rust, but it's mainly due to programmer choice. I wouldn't even say programmer error, because bugs are just a fact of life, and you're gonna have bugs in Rust and you're gonna have bugs in Go. You might go ahead and unwrap Rust took down internet. You might unwrap in your Rust program, and that's the equivalent of a nil pointer dereference. But you don't have people talking about, oh no, Rust nil pointer dereference. No, people have an idea of Rust being safer because this is sort of not the norm. You don't unwrap in Rust. People sort of look down on you if you unwrap. People know it's an unsafe operation. Whereas in Go, you know, the pointer type is not seen as an unsafe. It's not seen as unsafe. You know, it's sort of, oh, that's just the way we do things around here. And I guess I'm getting at it's like, it's a matter of how people in the ecosystem program. I tend to not use pointers because I know of their dangers, and just there's no real reason to use them other than for methods. So you'll see none of my types inside my struct are pointer, but they all have pointer methods on them because they need to modify their state. So I am using pointers, but I don't expose myself to the downsides of pointers. So it's like a very, I feel, smart, cool. I feel it's a cool trade-off. I don't want to call myself smart on YouTube. People are gonna eat me alive. What else? So yeah, I feel like Rust has gotten a good rap on reliability because the language sort of guides you, right, to the safety. And that's by design, right? Go also guides you to good design, but I feel like Go could have done a better job at guiding people to avoiding the pointer types early on, and we wouldn't have so much flack from nil pointer dereferences, which are more common in Go, arguably. I'm not sure, I haven't seen any data on it, but I mean, I would believe it. They're more common in Go than in Rust. Concurrency. Most languages have some form of support for concurrent programming, doing multiple things at once, but Go support is second to none. So yeah, you're preaching the choir here. Yeah, Go's nothing really. I mean, you can go but Erlang did something really cool with their Erlang threads, right? Erlang is always the language that's been praised for doing it better than any other language, but Go is just simpler. So Erlang is much more like correct. You have much more control over your units of execution, but Go is just great. I mean, it's just so simple. I feel like Go struck an amazing balance in terms of simplicity, integration in the language, because it really feels just seamless. You know, you can just go function, right? Any function. You can go any function and it just works. Yeah, I'd say it's the perfect choice for high-scale concurrent applications such as web servers, microservices, and embedded systems, which do mechanical system manipulation. That's something I talk about in one of my talks, Aerospace Go, and I think I also talk about it in this very early Embedded Fest 2021. I didn't have my mojo yet back then, but I do mention, hey, Go routines are great for controlling mechanical systems because the reasons I go into there. So basically, mechanical systems are very slow. You want to maybe sleep after you do something because you know it takes some time, and you don't want it to block your entire program. What you do is you create your Go routine strategically so that maybe you contain a process in a Go routine and it sleeps after opening a valve, and it knows it waits 20 seconds, it waits a second for the valve to open, and then it does something else, opens another valve, and it sort of does its process thing while you still have like your kernel of execution in your other Go routine, which is always checking sensors to make sure everything's fine. And if something gets out of line, it can send a signal to the process Go routine to end itself so that the main Go routine can take control and sort of return everything to a safe state. So that's what I talk about in these talks, my earlier talks. Back here, lightweight syntax is really nice. Blah, blah, blah. Go is so nice. Oh my God. Rust has most of the same concurrency features as Go, and in some areas, even better ones. For example, the ray encrate provides very elegant and lightweight way of turning sequential computations into parallel ones. Very cool. Also, many bugs in concurrent programs stem from the kind of memory safety errors that Rust was designed to eliminate. A good example is the standard library's mutex class in Go. You can forget to obtain the mutex locks before accessing something, but Rust won't let you do that before accessing. Oh yeah, so Rust does have this really cool wrapping, right, of the arc mutex, and you can be sure like, oh, I've acquired it and now I use it. I mean, you can do the same thing in Go if you wanted, right? It's not like Rust found anything special. Should I honestly, like, I really feel like, but maybe people are gonna doubt me if I don't show an example of how this would work in Go. So I'm just gonna create a file here. Bam. So main. So type mutex. So this is like your mutex in Rust, and you can have sync.mutex. You can do something here like m mutex t acquire func m.mu.lock unlock. And for more safety, in case your program panics, you do that and you do fen. And the way this is used, func main, right, you do vt m.v, you know, var m is mutex int, and you do acquire, bam, print, and this is a super safe print. You can be sure that you're the only one who acquired that that value. So yeah, and you can go to town on with this pattern. I mean, there's so many different ways to like acquire a mutex in a super safe way. You can make this return an error. So you're gonna forget to obtain the mutex locks before accessing something. I mean, if you're worried about that, do this. Rust also won't let you share data between threads unless you can prove the compiler it's safe to do so. And while this can be annoying, the discipline this imposes is something Go programmers have to supply for themselves, rather than be built into the language. I think I heard the Primogen talk about this and be sort of mock the idea of fearless concurrency, Rust meme. Formally correct. Okay, let's suppose that's true. Okay, let's give Rust this one. Okay, Rust is perfect. Unsafe does not exist in Rust, and it'll just always work. Unsafe, I mean, that's unfair. Unsafe does exist in Rust, so you could bypass this, but let's just suppose in the language, you're not gonna do that. So yeah, okay, maybe Rust wins here. I can live with that. Rust is carefully designed to ensure that programmers can't do something unsafe that they didn't mean to do so. Are you sure about that? Are you sure about that? What is it? Oh my god, I wish I knew more Rust, because I have heard this to be not entirely true, even without the use of unsafe. Overwriting a shared variable. I'm guessing if you protected your variable very completely by wrapping it in every single class you can imagine in Rust, then it won't happen. But then you have another problem where you're just wrapping everything in arc, mutex, everything, right? What was it? Is Rust common classes? Come on, give this one to me. I can't for the life of me remember it wasn't one of these. Clone? It was copy? I feel like it was like copier or clone. It's just one way of overriding this was to like just clone all your data instead of... Oh, well, I've forgotten. As a result, so this the compiler requires you to be explicit about the way you share data between different parts of your program and can detect many common mistakes and bugs. As a result, so-called fighting with a borrow checker is a common complaint among new Rust programmers. Implementing your program in safe Rust code often means fundamentally rethinking its design, which can be frustrating, but the benefits can be worth it when readability is your top priority. If you're a C or C++ programmer who spent weeks chasing down memory safety bugs in those languages, you'll appreciate Rust. Good. what's the point of a language that doesn't change the way you program after all? But there are other legitimate priorities. If you choose Rust, you'll need the guarantees the language provides: safety against null pointers and race conditions, predictable runtime behavior, and total control over the hardware. If you don't require any of these features, Rust might be a poor choice for your next project. That's because these guarantees come with a cost. Ramp-up time. You'll need to unlearn bad habits and learn new concepts. Chances are you will fight with the borrow checker a lot when you start out. Now, I'm going to pause. So on this, safety against null checks, I mean, you got the wrap method. Race conditions, okay, we gave Rust that one. Predictable runtime behavior, sure, more predictable than your regular Go code, but you can reach even more predictable behavior if you just think about your Go program and deal with not relying on the garbage collector all the time. Total control of the hardware. I wonder what that means. I guess, yeah, you don't have, I mean, you can compile without the scheduler, without the garbage collector in TinyGo. And there's now this new Goose is Noose, bare metal, Golang, add bare metal support. Once this is accepted, and there's a high likelihood it'll be accepted, then you'll have complete control over the hardware. Just something to keep in mind. This eliminates the entire dependence on the operating system. So you decide what compiles for your binary. The only thing remaining would be to be able to bootstrap your own runtime when compiling with native Go, but you can already do that with TinyGo. So honestly, once this happens, bam, it's go time. If you scale, Go was designed to make it easy to scale both your projects and your development teams. Its minimalist design leads to certain uniformity and existence of a well-defined standard style, meaning that any Go programmer can read and understand a new code base relatively quickly. When it comes to software development in large, clear is better than clever. Go is a good choice for big organizations, especially with many distributed teams. Its fast build times also favor rapid testing and deployment. Languages like Go, that feature garbage collection and automatic memory management in general, make it quick and easy to develop reliable, efficient programs. And for some people, that's the most important thing. Now, here we're, I mostly agree with this. Just Go is pragmatic, reliable, efficient programs, scalable. It's clear, it's understandable. Anyone you onboard will be able to more or less get the gist, even if they haven't programmed in Go before, relatively quickly. I have anecdotal evidence of this, but yeah, it's here too. So why take it from me when you can take it from Bitfield Consulting? Languages such as Rust, where the programmer must take explicit responsibility for allocating and freeing every byte of memory, are better for real-time or ultra-high performance applications. My friend. What we see here is Go outperforming Rust everywhere, all across the board, when the garbage collector is not involved. So if you know how to program Go without the garbage collector, and it's pretty much this, I feel like it's much less effort than trying to program in Rust, but it might not be the case for everyone. So if you can find the way or learn the way, because I have videos on this matter of using Go without the garbage collector, then Go may be better for real-time and ultra-high performance applications than Rust. I feel like Rust, in my experience, it has its niche set elsewhere. It's not exactly, being the fastest, but being the most correct and safest and most constrained at runtime, as in the type system is constraining you to do safe things. So Go is a very different language to Rust. Although both can vaguely be described as systems, languages, or replacements for C, they have different goals and applications, styles of language design, and priorities. Garbage collection is a huge differentiator. Having GC in Go makes the language much simpler and smaller and easy to reason about. Not having GC in Rust makes it really fast, especially if you need guaranteed latency, not just high throughput, and enables features and programming patterns that are not possible in Go. Again, guaranteed latency, high throughput. Yeah, if you're using the garbage collector, you're gonna have a hit. If you can do without it, then Go might even be superior to Rust in those aspects. Error handling. In some languages, when a function encounters an error, for example, something like file not found, it can be handled explicitly or it can be handled automatically, propagated back to the function's caller. You can I'll make that. The replacement here is it can be handled the right way or it can be handled the wrong way. Yeah, so program crashes with an ugly error message. So yeah, these are exceptions. It's talking about explicit errors as values. That's this. Or exceptions. Errors that trigger the automatic return from the function, if not handled, are called exceptions. And while convenient for programmers, can lead to some confusing behavior. I don't think it's ever convenient to use exceptions. People think they want exceptions. Why? Why do I think this? Because it's true. Go exceptions. Try catch. Issue. So this, or should I show you Sean? Go try catch. Sean. Can I find that website? Sean Liao's. Sean here. Go error. So there's been so many Go error handling proposals. People really want like a different form of error handling. Like people are not happy with this. When I say people, I mean a subset of Go. A very specific subset. Why do I say subset? Because even if there's been all these proposals to change how we do error handling in Go, none of these have been accepted. And I don't think any of these has been active at any point. There very likely has been some proposal that has been active, but wrap with stack traces. Most of Gophers agree. Some of these don't look like Go. Like this is not Go. I think the question mark garnered more support than other identifiers. Tokens. But yeah, none of this looks like Go. Honestly, there are some that do look like Go. There was one that actually got pretty far, but it was not accepted as of the Go team. No syntactic support for. So choose the one for the title. There won't be any error handling in Go, any error handling changes, because there is no clear consensus on the benefits. And I think this one actually made it quite far. My issue with this is like, what if you have a long function? It's on the end of the function. It's not visible. It's not readily visible, and it just hides away control flow, is how I feel about it. And I'm guessing a lot of people felt that way because we're not getting error handling in Go. So yeah, that's I went off track there for a second. We are not getting exceptions in Go because if used as a control flow mechanism, you are giving the third-party developer, so the guy person who's designing that third-party package, you're giving them control over what your program does, because you're basically telling them, oh yeah, sure, just throw an exception here, modify my control flow, and I'll have to deal with it. And that is insane from a point of view of reliability. Like maintaining programs that have an unknown set of exceptions where every statement can throw an exception is just nuts. There's just too much overhead for the programmer, in my opinion, and also in NASA's opinion. NASA prohibits exceptions. C++. So yeah, they compile C++ without exceptions on extraplanetary missions. So the Go team is not alone in being against exceptions as the main control flow. NASA is as well, and for good reason. Errors that trigger automatic return for the function are called exceptions. Yeah, not good. No bueno. In Rust and Go, while exceptions are available, their use is strongly discouraged. Instead, both languages treat errors as values. And if you use Rust or Go, then you know, yeah, we love the error is not nil. I kind of feel like not reading this because I feel like I know what this is going to be about. It's just like, oh yeah, we do error handling really good in Go and Rust. We love it. But hey, here's a point. Rust error handling is even more powerful, relying on built-in option and result types, which indicate a return value may or may not be present, or may instead be some error. For example, here's how we might write the previous example in Rust, and if getAnswer returns an option, indicating there may or may not be an answer. If let sum. So the reason I just smirked there is because this is if error is not nil. I'm not sure why they say it's more powerful. V comma error strict conv a to I. Do something with V. Yeah. This is hard to read, arguably. It's the same thing. And here, getAnswer, handle error. somehow. So this is basically like, let's try to replicate this in Go code. I know it might be kind of hard, but do something with V, handle error. And I mean, you can even do this if you want. It's the same thing. And your error is contained within the scope. So, no, not sure why they say it's more powerful. I guess, oh, because you can do this. This is nice. Syntactic shorthand. Cause a function to return automatically if the option value is not present. So this is what they want to add in this error handling proposal, where we saw the question mark here. Yeah, we basically want to copy Rust, and yeah, this is great. Some would argue it's hidden control flow. I mean, it's a single token on the end of the function. You might miss it. It's just weird. I mean, I really like explicit error handling, and this feels too implicit, honestly. If we implemented it, I might come to like it. Really, the limits to what I can develop do not depend on this question mark being there. That is not limiting my capacity as a developer, for sure. And if it is limiting someone's capacity out there, I'd like to, talk to that person and, get an idea of what it is about this that makes them go further. The history of computing programming has been a story of increasingly sophisticated abstractions that let the programmers solve problems without worrying too much about how the underlying machine actually works. That makes programs easier to write and perhaps more portable. But for many programs, access to the hardware and precise control of how the program is executed are more important. Rust aims to let programmers get closer to the metal with more control, but Go abstracts away the architectural details that let programmers get closer to the program. Now, I don't like how... Yeah, this is just false. I mean, I program microcontrollers with Go. I write to, memory mapped registers. Go doesn't let me get close to the metal. In any case, I mean, I've contributed to Embassy RS. And this is an example of I am so sorry, Dario. I'm about to dump on your project a little bit, but I feel like the Embassy has gotten the synchronization, the async part, sort of a bit too abstracted. If you looked at, so I had to look at don't get me wrong, this is I love that this exists because it was readable, is very readable. I was able to implement drivers I wouldn't have been able to implement if I were to look at the C version, because Rust is so much more readable. But I mean, I feel like this is an example of, hey, you can overdo your abstraction from the metal in Rust, just as you can in Go. So I'm looking for the CYW driver, which is, here it is. It does heavy use of async, and I feel like that's just not good. I'd much rather have a driver that is not asynchronous and use and leverage async functionality from the kernel side, if that makes sense. So write your drivers to be sequential, to be serial, not parallel, not concurrent, not async, and then use them from a networking stack, like, for example, Elneto, in a concurrent manner, using the serial or non-async API of the driver. I feel like this library just shoves the async into the CYW driver, and I feel you could have abstracted that a bit further up. So yeah, I mean, you can be close to the metal in Go, you can be close to the metal in Rust, and you can also choose to not be close to the metal in Rust, where you can be close to the metal in Go. I feel like that's a design decision. You can not use the garbage collector, you can use it. It's a programmer's choice, honestly. There's nothing limiting you from getting close to the metal in Go. You think you can understand Go code, but you're wrong. And you think you can't understand Rust code, and you're right. That's a funny quote. It's like a bait quote. I'm not gonna fall in that bait. Correctness. Go and Rust both aim to help you write correct programs, but in different ways. Go provides a superb built-in unit testing framework, for example, and a rich standard library, while Rust is focused on eliminating runtime bugs using its borrow checker. It's probably fair to say that it's easier to write a given program in Go, but the result may be more likely to contain bugs than the Rust version. Rust imposes discipline on the programmer, but Go lets the programmer choose how disciplined they want to be about a particular project. Yes. So if the programmer, yes and no, I'd say, because if the programmer is a very respectful and just devout Rustacean, yes, they will write less bugs. Maybe. Who's measured this? I don't know. But the truth is, Rust is hard for some people, and some people choose, shortcuts. This is something, I'm part of a few, I have friends, believe it or not, that write in Rust. And, it's a fun joke to say, oh no, I just cloned it. No, I just circumvented the type system to be able to get the value from that class, which was being too strict. And that's a real thing. People circumvent the Rust type system, and they, in the process, open their software to bugs. So I would not say that this is truth, factual truth. None of this is factual truth, right? It's like everything comes down to it depends. And in this case, I feel like it depends on the person. If it's between a devout gopher and Rustacean, maybe the devout gopher is gonna create more bugs because the Go ecosystem, the way gophers are taught, it's just pointers all over the place, and it's really easy to run into a nil dereference somewhere there. And devout Rustaceans are gonna leverage the whole type system to make sure that they don't run into bugs, and in the process, they'll leave the project to their children as inheritance because, you get the joke. So, conclusions. If you're new to the tech industry, getting some skills in one or both of these two languages should be your priority. If you're an established developer who doesn't yet have Go or Rust on your resume, I think you will be well advised to invest some time in acquiring them. I hope this article has convinced you that both Rust and Go deserve your serious consideration. You should reject the false dilemma that you can only learn one or the other. In fact, the more languages you know, the more valuable you are as a software developer. That is very true. That's where I can help. You can study with me directly through my professional mentoring program for Rust or Go. I also offer live Rust training for teams. Every new language you learn gives you new ways of thinking about problems, and that can only be a good thing. The most important factor in the quality and success of any software project is not the choice of language, but the skill of the programmer. You will be most skillful when using the language that suits you best and that you enjoy programming in the most. So the question is, should I learn Rust or Go? And the only right answer is yes. That's a nice finishing conclusion. Overall, one of the most informed articles I've read, or just unbiased, I'd say. It just really tries to evaluate Go and Rust for what they are. And when I say for what they are is, the public perception that Go is, the public perception that Go, you can only do Go with a garbage collector, and garbage collectors have interruptions and blah, blah, blah. Most people are not aware that, hey, we have TinyGo, a compiler that runs faster than Rust when there's no garbage collector, and you can program without our garbage collector in Go. Yes. And also, Go has been shown to be real-time. So no jitter, predictable runtime somewhere here. Oh, okay. You can watch this video. Here, TinyGo shows no jitter on this paper. All right. And I think that's it for this article. Really good one. Oh, it's really just dived into all the points. One should really review when deciding on one language or the other. And I do agree with this last statement. Hey, if you enjoy Rust, go for it. Rust is a great language, and it does give you so many benefits. Personally, I'm here because I want to just raise the flag of awareness that, hey, you can Go deserves much more credit where credit is due, thanks to the presence of TinyGo and new programming techniques like avoiding pointers in your structs and avoiding a heap, no garbage collector, using that printAlex flag. So with that information, I hope you are ready to decide whether Go or Rust is suitable for you. Thanks for watching, and I'll see you in the next one.